Another application of mixture models that is very important in practice is clustering. Clustering is sometimes called unsupervised classification in the literature. If your training is in machine learning, you will be more familiar with the unsupervised classification term. If your training is in statistics, you may be more familiar with the clustering term. The idea in any case is to partition the sample that you have that comes from a heterogeneous population into homogeneous groups. So the idea is to generate these homogeneous groups that we're going to call clusters. And this is important for a number of reasons. For example, in biology, you may be interested in finding groups of individuals that correspond to a species according to how they differ in some physiological characteristics. So a clustering tool allows you to create those groups or to find out those different species out of the samples that you get from, for example, measurements of length or weight or other physical characteristics that may be relevant. Now, the literature on clustering is very extensive. There are a lot of tools out there for carrying out clustering. One of the techniques that is fairly commonly used is called k-means clustering. And you may be already familiar a little bit with it or have some experience playing around with k-means clustering. K-means clustering is closely related to mixture modeling, and I want to illustrate that connection before showing how the mixture models can then be used to extend and improve over what k-means clustering does. Now, the idea behind k-means clustering is if you start with a sample that looks a little bit like this. So this is one variable and this is another. I'm going to assume that you only measure two features for the individuals. So this is our whole sample, and these groups here are the clusters. So in this case, we're going to have 3 clusters. So the idea of k-means clusterings is to make a guess. You have to fix k. You have to decide how many clusters you want. But once you have decided how many clusters you want, you're going to start by setting up some cluster centers, say M1, M2, and M3, where M sub k are cluster centers. And then you're going to have some membership indicators. That are very similar to the C sub i's that we had used both to derive the EM algorithm and the MCMC algorithm for fitting mixture models. This SI just tell me to which cluster each observation belongs. And what we do is assign observations to the closest cluster center. So if I'm trying to decide to which cluster this observation belongs, I'm going to look at this distance, and this distance. And because the distance to M2 is the smallest, then I'm going to decide that this observation in particular belongs to cluster 2. So I'm going to make the SI corresponding to this observation, I'm going to make it equal to 2. And then I just repeat. So now that I know what observations belongs to each cluster, then I just recompute what is the cluster center. So I will put this into an algorithm in just a minute, but the rough idea is to iterate between assigning observations to clusters and computing where the center of the cluster is. Now let's go back to mixture models for a second. So if you remember, we had this variable C sub I, in the case of the mixture models, that were component indicators. And in the particular case of the EM algorithm, which I'm going to use for concreteness for illustration, we had also these variables b, I, k that just reflected the probability that c sub I is equal to component k, given the current parameters of the model, the current estimates of the parameter in the model. So given the vector omega and the variables, the component-specific parameters theta. And we computed this using basically Bayes' theorem back when we derived the algorithm. So these components could be interpreted as the probability of observation I in component k. Now, we never, in particular with the EM algorithm, we never explicitly provided an estimate for the CIs, but it's clear how we can go from the estimate of the BI case to the estimate of the CIs, which is basically to pick C sub I as the index k that maximizes the probability, so just the mode of this distribution over components. So we could make C sub I be the arg max over k of the BI case. So if we have a data set to which we fit a mixture model with k components using the EM algorithm, once the algorithm has converged, we have the values of the omega and the thetas, but we also have the value of the b's. And one way in which we can use the value of the b's is by basically picking what is the component that generated the observation by looking at which one of those b's is the largest and looking at what component that corresponds to. So this would allow us to use mixture models to do clustering to basically generate or decide which observation generates each component. So now let me write side by side how the EM algorithm for one particular case would look like and compare one particular mixture of models and how that would compare with the algorithm for k-mean clusterings that I was describing just a few minutes ago. Let's start by first describing formally the algorithm for k-means clustering. The algorithm for k-means clustering has really two steps. The first step is what we could call an assignment step, where we decide which component each observation belongs to. So we decide on the S sub i's. And the form of that step is such that we make S sub I equal to the arg max over k of the distance between each observation and the case center. And this refers to the Euclidean distance. So typically, we're going to be working with multivariate responses here, like in my previous example where I had 2 dimensions. So in other words, we compute the distance between the observation and each one of the centers, and we do the arg mean. So we take the one with the minimum distance. The second step that we do is we do a center update step. So this would be iteration t plus 1, and this is based on iteration t. And in this step, what we do is we get the new cluster centers by basically just averaging all observations that belong to the component k. And one way to write that is by saying, well, what I'm going to do is take my sum in principle over all the observations of x sub i's, but I'm going to add an indicator function that s sub I is equal to k, and I'm going to divide that by the sum from 1 to n of the same indicator function, Si equal to k. So this is just a fancy way to say I'm just going to take of the n observations, these terms are going to be different from 0 only if the observation is in the kth component. Otherwise, I have the observation multiplied by a 0. And similarly down here, this is just counting how many observations are in the kth cluster. So this is the average value of the observations that are currently assigned to the cluster. So given some value, some initial value for the centers, we can just alternate between these two steps until convergence. In particular, until the membership of the observations to the cluster doesn't change from one iteration to the next. Now, let's compare this against an EM for mixtures. And let me, in particular, consider one very specific mixture. So consider a mixture in which we have k components, just like we would have in the k-means clustering algorithm. But rather than working with some general weights that I'm going to try to estimate, I'm going to simplify the mixture a little bit. And I'm going to say that all my components have the same weight. So I'm going to make it 1 over k. This would be my omega k for all k. And I'm going to use Gaussian kernels, but I'm going to use a very particular form of the Gaussian kernel. So this is going to be 1 over square root 2 pi sigma to the p x of minus 1 over 2 sigma square norm of xi minus mu k square. And if you look at what this is, this corresponds to the kernel of a normal distribution with mean mu sub k and with variance sigma square I. So rather than So this is even simpler than some of the settings that we have worked before. So we have worked with cases where we allow the variance covariance matrix of the multivariate normal to be general. We have worked with cases where, and vary with the component. We have worked with cases where we make it be the same for all components, but we still allow it to be free. Here we're working with a very particular setting in which we're restricting it to be spherical, so to be sigma squared multiplied by I. So we assume that all different dimensions of the problem have the same variance. And this is going to be very important for some of the discussion that we're going to have at the end. So I'm going to be working with this particular mixture model and the EM algorithm for this particular mixture model. And if you, again, remember, you have in the EM algorithm an E step that in this case takes a very specific form. So we're going to make our BIK in step t plus 1 to be proportional to, because the weights are the same for all of the components, then I don't have to worry about them. It's just part of the proportionality constant. And 1 over square root 2 pi sigma is also going to appear in every kernel, so I also don't need to worry about that. So I can just write the rest of the expression, that is exp minus 1 over 2 sigma square norm of xi minus mu k square. And you can start to see some similarities between the two expressions already. The other step is the M step. And in the M step, you have two pieces. You have one piece that has to do with updating sigma, and one piece that has to do with updating mu. But let me write explicitly only the one that has to do with mu. And if you think about how you do the update of mu to the next iteration, this was something very similar to this. It was a weighted average with that weighted average being given by the VIKs. So you had the sum of BIK in step t plus 1 multiplied by x sub I, sum from 1 to n, from 1 to n, BIK t plus 1. Again, you can clearly see the similarities. So let's explore this a little bit more. So the first thing that I want to note is that when we discuss how to select the C sub i's based on the V sub i's, what we discussed is that we would choose the C sub i's so that we maximize the probability. But maximizing this quantity should be clear. It's exactly the same thing as minimizing this quantity, because the exponential is a one-to-one function, and in particular an increasing function, and we have a multiplication by a minus, so that changes maximization for minimization. So there is a clear analogy to this, and in particular when you have components that are very well separated from each other, we have seen that these VIKs are all going to be close to 1 for the observations that are in that component, and close to 0 for observations that are in other components. So essentially, that means that these two steps, if the components are well separated, these two steps essentially give you very, very similar results in terms of the allocation. And if you think about the second step, something similar happens. As I just said, if the components are well separated, these VIKs are, for the most part, either 1s or 0s. And in particular, for a given I, there is one of them that is going to be really close to 1, and the rest are going to be really close to 0, which means that you are essentially just replicating this weighted sum where the weights are 0s and 1s. So this is just to highlight that running your k-means clustering algorithm, it's very similar, and it's going to give you results that are really, really, really close to the results that you would get from running an EM algorithm for mixture models for this particular mixture up here, where you are mixing Gaussian kernels that have not only a common variance across the kernels, but also a common variance along the components, and that assumes that the components are not correlated. Again, why is all this discussion important? Well, because it highlights what are the shortcomings of k-means clustering, and it also suggests some ways to address it. Let's elaborate a little bit more on those ideas. Let's consider this mixture model here. If you think about how densities from that mixture model look like in the two-dimensional case, they are going to be, the contour plots for these densities have to be circles. And they have to be circles of about the same size. So you're expecting your clusters to look something like this. When you fit a mixture model of this type. That won't be a very good idea. So this is what k-means clustering expects to see. But in practice, your clusters may not look anything like that. Your clusters may look more like a bunch of points like this, and then a bunch of points like this, and then maybe a few points like this. If you're going to make a guess about how the contour plots for these densities locally look like, it's probably something like this, and maybe something like this. So this clearly looks like a circle. So for the purpose of this cluster, k-means may do a reasonable job. But if you think about these other two clusters, they clearly show, first of all, that there is a correlation between the two variables, between x1 and x2, between the two features. So that's something that k-means clustering can't really deal with. And the other thing that it shows is that you have a different variance in each one of the two dimensions. So one of the variables has a much larger variance than the other one. And that is clearer here, where you can see that x1 for this cluster varies very little, but x2 for this cluster varies a lot. So the fact that k-means uses this structure means that it will typically do a poor job at clustering when you have situations like this. The other thing to observe is that in k-means clustering, you are assuming that the weights for each one of the components is the same, and it's 1 over capital K. What that essentially assumes is that you're expecting about the same number of observations in each one of the clusters. Again, if your real data looks a little bit like this, where you have one big cluster where most of your observations are, and then maybe you have another small cluster here with just a few, k-means clustering will typically have a really hard time separating these two clusters, because it wants to move some observations that are in here to this side in order to make the two sizes the same, so that this assumption that the weights are 1 over k for all of the components is correct. So by casting k-means clustering in the context of a mixture model, we can see clearly what the shortcomings are, and obviously we can see clearly how to deal with those shortcomings. For example, if instead of working with sigma square times the identity matrix, we work with a general matrix sigma k here, we allow the components to have different shapes. So that would be a way to deal with this problem. And then by working with these more general weights, omega k rather than 1 over k, you can deal with this problem down here. More generally, you can deal with other problems by changing the type of density that you use for the mixture. For example, it's common to replace the normal distribution with something like a t-distribution or some skewed version of the normal distribution to capture other features that in a particular data set may be present in the data. So by presenting it in this context, we have a number of generalizations. The other generalization that we can easily obtain by thinking about clustering in terms of mixtures is to generate Bayesian procedures for clustering. And in particular, we discussed feeding this model using the EM algorithm and how that looks like k-means clustering. But if instead you fit this model using, for example, an MCMC algorithm like the one we discussed in the past, then what you get is essentially a Bayesian k-means clustering algorithm. And more generally, you can get powerful Bayesian clustering algorithms by considering more general mixtures that are fitted using algorithms such as the MCMC that we discussed a few lectures ago.